Once we have reduced the space, the dimensionality, then if we pick the dimensions where the data was being distinguished nicely from one from another, then using KNN we can easily do the actual classification. Okay. Another concept to know about the PCA, and we have talked about it before, is, okay, let's say we have some data over here. Okay, looks like this. So these are our 200 faces, right? After we've applied the PCA. If we now take a look at our basis vector corresponding to the highest eigenvalue, it will always be pointing in the direction of the data. So it will always be pointing. So this is the basis vector. Corresponding to highest eigenvalue. Okay, or if I try to show you, pretend this is the data, right? Okay, see if I projected it, let's say on the x-axis. Okay, then what's the difference between these two data points, large or small? Small, right? On the other hand, let's say I move this in this direction. And now I try to project this and this. Now what's the difference?
Would be large.
It will be large, right? So the basis vector corresponding to the highest eigenvalue gives us
A vector.
the highest variance. In the data. So in that direction, there's highest distinction between the data. Okay, so that's the reason PCA works and the reason it can be, and of course the next vector will be orthogonal to each other. So if we had a distribution like this, the highest eigenvalue vector will be in this direction, the second highest eigenvalue vector will be in this direction, and if we had, pretend this is like a three-dimensional object with another certain width in the third dimension, then the next vector will be in the z direction. So each one of those 30 bases that we came up with tells us which direction the data can be distinguished best from each other, right? Okay, so now to give you the motivation for the LDA. Okay, the drawback of the PCA is, see, when we assembled it, when we assembled the I matrix or we computed the eigenvalues, did we ever tell it which one is which person?
Never.
Never. So that's why this is called unsupervised learning. Okay, when we are creating the basis vectors, it has nothing to do who's who. Okay. Of course, once we have computed the bases, then we can project the incoming data, and then using KNN we can find who's who. But the fundamental technique doesn't bother about it, right? Okay, so let's pretend this was our data, right? Let's pretend one of these is person X. Okay, let's pretend this one also happens to be person X. Or let me pick another one. This one happens to be person X. Okay, my question to you guys is, if it is the same person, should the projection produce answer close to each other or far apart from each other? Close to each other, right? But if they are two different people, then what do we want?
Large.
Then we want the large difference, right? Okay, so this is where, so the PCA doesn't care whether it's person X or person Y. So even if it's the same person, it will try to move them far apart, because that's what the fundamental, the highest eigenvalue vector tries to do, moves the data farther from each other so that we can distinguish one from another. But if they're the same, so in plain English, our goal should be keep data belonging to same class, meaning same category, closer or farther?
Closer.
Closer. And data belonging to different class, okay, farther from each other. Okay, and PCA does not do this. PCA makes everybody farther from each other, right? Let me, to save time, somebody had a very nice PDF for explaining the LDA via simple examples. And with your PCA background, now you should be able to understand it very nicely. So let's go through and
Here in the 200 images, it's better for PCA if they are different. We don't put same person, like 5.
Are they all the same
Yeah,
people?
but let's pretend these 200 were actually 40 different people. 5 of the images were belonging to the same person, but taken under different conditions. Like, you know, some maybe in the gym, somewhere you were in the dorm or something. So if we applied the PCA, even for the same person, it will try to move them apart as much as it can, because we never told it who's who. Oh, before I go there. Okay. So the code, it's already on the website, is on the MNIST data. So I'm showing you a KNN example on MNIST. And most of you already know MNIST, but MNIST is basically a digit recognition data set. Okay, each digit over here is 28 by 28 pixels. So like there's 0, for example, there might be 102, 28 by 28 pixels, right? So if we assemble it into a vector, it becomes 784 by 1, because 28 by 28 is 784, right? And in this data set, there are 10,000 training characters or training digits. Sorry, 60,000, not 10,000. 60,000 training digits and 10,000 for testing, which are not in this data set, in the training data set. Okay. So the code that I will show you in a second, so this is a C# code. Okay, first thing it does, it converts, reads the images, converts them to a 784 by 1, right? Then all 60,000 of them. So essentially, and it stores it in some kind of an array. Okay, so think of it, all of these are now points So there are 60,000 points in the 784 dimensions. Okay, so now we go to one of these 10,000 testing images. We also produce a 784 by 1. Okay, so now what will we do? We'll do a Euclidean distance with all 60,000 over here. Okay, and then we'll sort them by distance. So if k is 3 in our KNN, then we'll take a look at the top closest 3 by distance, Euclidean distance. And suppose this says digit 6, digit 6, digit 5, then what's our answer? 6. And if that indeed was 6, our accuracy count will go by 1, right? So anyway, it takes a long time. So in the beginning of the lecture, that's what I was doing. I was running this code, but 5 minutes ago it got done. Okay, and so I'm doing it on the entire 60,000 training data, not 1,000 that you guys used to do in the deep learning class. And if you take a look, what's the accuracy over here? 96.88%, which is pretty decent. We didn't even apply any PCA or anything. Okay.
That's the KNN alone?
That's a KNN alone. Okay, doing nothing basically, just Euclidean distance. But this is on the entire 60,000 data. So remember, you guys were doing it only on 1,000. So as part of your assignment, you know, because rather than you running your CPU for a few hours, I'll have you do it on the 1,000 training, not 60,000. So you might get 84, 85%, then you'll apply the PCA, then you will see, oh, it becomes better. And then you'll compare it with your deep learning approach, okay? And then, remember I started on the CNNs.
Yes.
Then once I show you the CNNs, and you'll see that will go fantastic, okay? Anyway, so once it's trained, right? So as part of this program, for example, I can go here. Where was my data? Okay, so for example, I can pick any digit. Okay, let's say I pick 3 over here. Okay, so again, what it's doing is matched label 3 as an example. So that's what it's saying. Okay, so now again, it's looking at the neighbors. So you will play with the values of k. K of 3 may not be as accurate if you made k of 5. It will, meaning you're looking at the 5 neighbors and doing the majority voting. So it will be a little better. Okay. Okay, so anyway, so this program is on the website. It's under, I forgot, 2017 lectures, but I'll move the link to 2019 as well. Okay.
What's it going to be posted as? The name of it?
Name of it will be like KNN classifier or something on MNIST.
Professor, can we say higher the K value is better the results, or how to choose the optimal K value?
Generally, around 5 is pretty decent. 3, like I said, may not be as good. More than 5, it really doesn't help that much. You know.
We should try.
Yeah, you can try. Yeah.
Professor?
Yes.
You got 96.88% accuracy using the KNN with no previous PCA
Correct.
on the, let's say the 100 by 100 on the 10,000,
Correct.
just by doing Euclidean distance.
Just by doing Euclidean distance between the unknown and seeing what are the closest neighbors from distance point of view and picking the majority of, if majority of those are saying 3, then answer is 3 as an example.
So but the neighbors from my understanding before, when we were doing KNN after the PCA, when we were checking the neighbors, we were using the basis vectors as a reference to check, oh, that is person Z, that is person X.
Okay.
So here, how do you check what are the neighbors that matter?
Because each image is already a polynomial.
Okay, let me draw an example.
Each image is already a polynomial.
Okay, so pretend these are, okay, the 60,000 data points, right?
Yes.
We don't even have to draw them. We just store them as a 784 in this case, 784 by 1 vector. And we stored the 60,000 points in some kind of array, right? Now we give it an unknown digit. We convert the 28 by 28 to 784 by 1. And we now do a Euclidean distance with all of them. And we pick the top 3. Distance, meaning the closest 3.
Closest to, yeah.
Okay, because we already know the labels for these, right? Meaning for each one of them we know which, because this is our training data.
Yeah.
Whether it's digit 5 or digit 7. Now suppose the closest 3, one of them says 5, another one says 7, another one says 5. So, and if indeed was 5, we increase our check mark. Now let's say one of them says 5, one of them says 7, one of them says 3, right? But indeed it was 7, then that's not inaccurate because there's no majority over here, no consensus. So that's like misclassified. So if we did that, we got 96.88. But that's again on the entire 60,000, on the entire 10,000. But still, it's very remarkable that without doing anything, it does such a good job.
Yeah.
It's
I was thinking,
better than.
I was thinking it could, let's say, in our, I know all the 60,000 points are going to be different, but we're looking at
The closest 3 to the
no,
input.
I'm saying we're looking at, we're studying a sample that has big variations across just 9 digits. Let's say we did this on like a background of 500 images of people's faces. Would the accuracy go down?
Correct. Because see, if you take a look at the MNIST data is the easiest data set because the background is always black.
Yeah, exactly.
Right? So you have a good point. If we did it on faces, and if we had 60,000 faces, it will hardly give you 30% accuracy.
Hardly 30?
Hardly 30, yeah.
So that's where it can be useful to do such as PCA.
But if you do a PCA, it will go up to at least 80, 85 or something like that.
But still, the deep learning approach would be more better than
Deep learning, as I will show you towards the end, nothing beats deep learning. Not even a human. So yeah, it's matching past humans.
So if deep learning approaches are beating it by such distances, why is there so many still opportunities out there with machine learning jobs?
Because that's a good question, because we only are able to do individual identifications, like we can recognize faces, right? But then again, I'll show you as an example. Maybe next time I'll run it and show it to you, my deep learning. If I'm in front of the webcam, it will recognize me. Okay, now what I do is I put my hand over here. So it recognizes me as some soccer player, I forgot. I was pretty happy. In fact, what you should do is, if you get time, if you go to YouTube and Joshua Benji is one of the top 3 people in the AI field, and he gave a presentation. I'll try to locate it. It's very, I mean, he doesn't go into any details of anything. He's just talking about what is the state of the art now, and what are the problems with deep learning, and where we need to go further. So one of his very, very important points, which I completely agree, is that and you guys can relate to it, right? So if we, for example, give it, we talked about the autoencoder as an example, okay? We give it some data, it will do a compression, and then it will do a decompression, right? So suppose it has learned it properly. I give it a 2, recognizes a 2, right? Okay, now I remove this. Remove the compression part and artificially give it some compressed data, okay? Which doesn't even, what I'm trying to say is, it was not even generated from a 2, it was generated from random noise as an example. But I can make it reconstruct as a 2. So his biggest, the most important point he's trying to come across is the way the deep learning is recognizing things is based on an abstraction which really does not relate to the actual object. So that's why we can fool it so easily. That's why I can put my hand over here and make myself appear like, you know, Ronaldo or somebody. So he's saying we should be able to, so the way we are treating deep learning, let me give you another analogy. Like, let's say, if you take a look at us as humans, right? What's our compressed, so let's pretend we as a whole is our input image. Once we pass it through an encoder, we compress it. What is that part in a human? Our DNA, right?
Oh, sure.
So if a crime is committed, for example, right? Just by looking at the DNA, can't you know exactly who did it?
Yes.
Yeah. Will the DNA of a person, not only a person, will the DNA of animal match with the DNA of a person?
It's
No,
unique.
it's unique, right? But in the deep learning field, think of our compressed code over here that we pass through a neural network, right? If we had 100 neurons over here, we give it 784. Essentially, it is compressing it to 100 values. Those 100 values, what I'm trying to say is, even if we give it a cat or somebody else, it may come out to be same as the 100 compressed values from a digit. But it shouldn't be. This DNA should be unique for everybody.
But it's not.
So it's not. So to summarize, why is there so many deep learning jobs? Because we are just scratching the surface of it. It can easily be fooled. Second comment I'll have is, we are only able to do individual things like recognize a car, recognize a person. But we as intelligent beings, we plan the whole day out. Okay, now we'll go to the class. Now we'll study this. Can a deep network do that? No, it can only do just one thing. So how do we make it do a sequence of activities? Hopefully in 5 years we'll be able to do that, then robots will replace us. So
You think the problems that you're talking about in deep learning, machine learning algorithms have some of those features that deep learning can't have?
No, see, machine learning, deep learning, even the PCA, like I said, we knew PCA at the mathematical level, but then we wanted to make sure that we can do it, we can learn the PCA automatically, and that's what the encoder does. So deep learning, basically, there's 3 parts to it. Let me put it this way. The first part is take the traditional algorithms, like PCA, like LDA, like support vector machines, and convert it to deep learning so that we can do a better job than we did before. Okay, second part is be able to do individual tasks, okay, such as recognizing lanes, recognizing cars, recognizing traffic. Okay, now let's go to, for example, self-driving. So we are able to put together a sequence of things, but not like a sequence at a much higher level, like a person, okay? Where you go to the grocery store, you pick up things, you bring back, then you cook. Can machines do that? So that's where we are heading towards, but we are not there.
Here, after conversion, after conversion, it is not unique, but for BCA, after basic
No.
vector, it is unique.
It's unique for our digits, right? But what I'm trying to say is, if I generated, I keep trying, and that's where I talk about these generative adversarial network. I can keep feeding a random noise to it, which doesn't even look like a digit, and have it produce the same compressed data as a digit.
But for BCA, it is difficult to have this problem because the basic vector are orthogonal. So we will not have this problem in BCA, right?
For the PCA, can we create artificial data so that we project like a known data? Let me think about it. I think we can still fool a PCA. But let me think more about it.
So if it can be fooled, so we can use BCA before deep learning. That we can challenge the field. The most important feature.
Okay, let me, that's a good question. I'll just give you 1 minute comment, then we'll continue from here tomorrow. Okay, so the question was, okay, I'll give you, and I'll demonstrate this to you later in the course. Okay, let's say some person comes in. Okay, we feed it to our deep network, and it recognizes as person X. And let's pretend it's doing a great job. Okay, now like I said, this person comes, covers part of the face. So then this deep network says, oh, it's person Z, which is totally wrong. So the question is, or even if it's a noisy data, it's noise, it doesn't even look like a face. We feed it, and somehow if this noise was created in a smart way, it will say this is person Z, which is really totally wrong, right? So the question is, as you were saying, if we use PCA before, can we eliminate this? See, these days we are trying to do everything using deep learning. So let me give you the solution, which you guys will also be learning. There's a class of networks called Siamese networks. Our next lecture in deep learning where what we do is we give it two things. Two images as an example, and all it does, it tells us whether they are similar or not. So in this case, coming to your question, let's pretend this was the recognition network. So somebody who is very crafty, they came up with a very random picture, and now it said it's person Z. Now what will we do?
We will feed Siamese network by that noise. And
So it recognize person Z, right? In our database, do we have a picture of Z?
No.
Yeah, we do. That's why it said it's Z.
Oh.
So can I feed picture of Z over here now?
yes, with the noise.
And with the noise, what will it say?
No.
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 Not so.
So we have one way of safeguarding it. Okay?
But if
And yes,
if
go
you
ahead.
apply BCA and if we cover his face, so in BCA we take the most important features. So
Right,
this,
even
for
PCA
example,
might say, oh, it's now matching close to person Z. So it's, right? So anyway, so it was good discussion, but we will continue on the LDA on the next part. I mean, next Wednesday.